Hello, my name is Anton Schmeigen. I'm a partner solution architect with Amazon Web Services. I'm thrilled to co-present today the industrial IoT anomaly detection and response demonstration with our advanced tier partner Klika. I'm joined today by Dr. Konstantin Meshcherikov, solution architect from Klika. In this short presentation, Konstantin will explain the unique positioning of proposed reference design among other AWS offering for industrial IoT, like Monitron on one side of the spectrum and AWS IoT Sitewise on another one. Then I will briefly walk through the architecture on both edge and backend services that deploy in the cloud. And finally, Konstantin will go through the demonstration of everything in action. Konstantin, can you tell us a little bit about Klika and how you work with your customers to come up with this reference architecture?
Thank you, Anton. Absolutely. Headquartered in Miami and with offices in New York City, Berlin, Almaty, Rostov, and Minsk, Klika is a global Internet of Things solutions development company. Klika co-creates end-to-end hardware, embedded and software solutions for wearables, smart home, buildings and city platforms, connecting healthcare, smart retail, connected agriculture, asset tracking, automotive, smart mobility, and cloud IT hub integrations for mid-level enterprises and Fortune companies. We are AWS Advanced Consulting and IoT competency partner with several AWS service delivery designations, including AWS IoT Core.
Thank you. So going back to the architecture slide, our journey starts when we deploy all hardware pieces on site and we instantiate cloud backend through CloudFormation template or CDK. AWS IoT Greengrass establishes connection to the cloud, and we can deploy and manage the lifecycle of components running on our STM32MP1 gateway. At this time, STM32WB boards establish connection through the BLE to the gateway running Greengrass and continuously sending the sensor data. Depending on your application, you can send the data continuously or put the end devices into the deep sleep mode and burst the data samples on some regular basis to prolong the battery life. So gateway process the data, and stream managers send the feed of the raw data to the Amazon S3 bucket. You can train your model using SageMaker Jupyter Notebook, and because it is a managed service, you really focus on the data science while the entire infrastructure is managed for you by AWS. When our model is ready, we send it to the ML model bucket, and we can further optimize it using Amazon SageMaker Neo, which is the service that compiles the model for particular architecture and also will be able to optimize it further, for example, do some quantization. Now you can deploy the model to your fleet of gateways and either send the sensor data to the time stream or display the data on Amazon Managed Service for Grafana, or stop the sending data to the cloud and just use SNS, anomaly detection, and notification. The crown jewel of this design is AWS Greengrass version 2, which is our latest release. Since initial release, Greengrass offered secure messaging bus, local compute, streamlined ML model deployment to your fleet, over-the-air updates, secret manager, and identity broker. But the biggest ask from our customers was that they need more flexibility. The latest version of Greengrass is version 2, and it is very elegant design indeed. So the main focus was given to the orchestration and coordination of component deployments, for example, dependency resolution. It's also very self-sufficient, reliable, and has an element of self-healing. Additionally, it has a really modular design and it's very flexible. You can deploy Lambda function, Docker containers, even VM if you like. It has very minimalistic core services. Technically, the only two core services you need to run the Greengrass version 2 is the nucleus and the CLI. And finally, we make it really extensible because there are no single IoT solution that I would say the same as another. So it really enables you to build the solution as you want it, as you need for your particular deployment, for your particular fleet of devices. I put this link for the fantastic presentation by James Gosling when we introduced Greengrass version 2 on reInvent. So he's going in much more detail through the design. With that, I will turn over to Konstantin to showcase how the solution works in practice. Konstantin?
Thank you, Anton. So for our demo, we decided to show how anomaly detection would work for a simple 3D printer you can see here. First of all, let me talk about the devices that collect the data. For this task, we needed a device that would be easy to connect to the equipment and start to collect the sensor's data. We did not want to add unnecessary wires as it would complicate the setup considerably, so we looked at the wireless protocols. We have decided that using Bluetooth Low Energy is the most reasonable choice. We have chosen the STMicroelectronics WB55 boards as data collection devices. They have good support and have some additional nice benefits. The first such benefit is the software ST provides with the boards. We did not want to reinvent the wheel and create and debug custom sensors data transmission protocol. Fortunately, ST provides a good solution for this task. The BlueST protocol provides Bluetooth Low Energy GET services to transmit streaming data from different types of sensors. There are libraries for STMCUs that provide the implementation of this protocol, a Python module that gives a nice interface to collect it, and even a mobile application to display and log the data, which is invaluable for debugging. We also wanted to separate data collection from the transmission on the WB55. While it can be done using a relatively simple state machine, it would make the possible extension unmanageable, so having an RTOS on the board is definitely useful. WB55 is fully supported by FreeRTOS operating system and even AWS qualified, so it was a natural choice for it. Now let's move on to the second, I would say the most important part of the solution, the Edge Gateway. We envisioned that it will take the responsibility for virtually all computations that are needed for the task. By having all computations on the gateway, we decrease the latency and minimize the operational costs. However, managing all the software that is needed is a really complex task. The different components of the solution need to be orchestrated and communicate with each other. Furthermore, they need to be updated when the new functionality is required or the anomaly detection model is retained on the new data. AWS IoT Greengrass can help with this task. We use the STM32MP1DK2 board as a gateway with the Yocto-based Linux distribution running. AWS provides the Meta AWS Yocto layer that has recipes for AWS software, including Greengrass. Let me briefly talk about Greengrass. The main building block in the Greengrass system is a component. You can think of a component as an arbitrary package of files that can have executables, but also can be just a bundle of resources. So there is great freedom of how you can build and update your system. Such an approach is very versatile. The only thing you need to additionally provide is a recipe that describes your components, their configuration and dependencies, and has some other information. Having the component system is indeed useful, but Greengrass provides several standard components and services that let your component interact with each other and the cloud services. One of such components we employed heavily in the solution is the Stream Manager component. It provides a message queue functionality that allows you to reliably transmit messages between different components. It batches messages if necessary to make processing more efficient. How it is done, I will show a bit later. Right now, it is important to add that it has functionalities that allow sending data to several AWS cloud destinations such as S3, IoT Analytics, and Kinesis. We use this integration to collect the training data and the model. All components with the versions, settings, and configurations make a deployment. Using this mechanism, you can control what software runs on which devices and change device roles from the cloud. So, for example, it allows you to provide your customers with pre-provisioned gateways that will also assume different functions later. Now let's look at the components we used in our solution. You can see the actual deployment with all this version on the screen. The first one is Bluetooth energy receiver component. Its purpose is simple: to collect the sensor's data over Bluetooth energy and send it to the stream to be consumed by other components. Working with Bluetooth energy using Greengrass is as simple as it is with any other software. You can use any libraries which work with Bluetooth. You should be aware, however, that it requires a privileged access, which Greengrass can also provide if the component's recipe demands it. Another thing is that most Python modules require the native helper executable to work. That means that you need to either cross-compile the module and embed it to your component or back it into your operating system image. To see this data, we use the Bluetooth BlueST SDK module. To send the message to the stream, you need to first create it. You do this by creating a message stream client and calling the create message stream function with the stream name and other parameters. After, you can just send arbitrary message in the form of raw bytes using the append message call. These messages can be read by other components using the read message call. So we have received the data from sensors and we sent it to the stream. To support anomaly detection, we need to do two things. First, we need to collect the training data in an S3 bucket, and once we train the model, we need to preprocess the data so the model can consume it. If we had a cloud-based solution, the natural way to collect the streaming data would be to employ the Kinesis Data Firehose service, potentially sending the data to it from IoT core using IoT rules. It would batch and preprocess the data and write it to the S3 bucket in the format of our choice. You still can do this using Greengrass. You have several ways to do this actually, but you have decided to keep as many computations as possible on the gateway, and luckily we can easily reproduce the functionality using the stream manager capabilities. First of all, we can have batching simply by telling the stream manager client read messages functions that we want to read at least several messages. In some cases, it would be enough, but we need to send the same data to the anomaly detection model, and we cannot have big delays for it. Thus, a second batching layer was implemented. We store the collected data to CSV file, and once a predefined time interval, we use stream manager integration with S3 to upload it to the cloud. To do that, we create two special kinds of stream. The first one receives the names of files to be uploaded, and the second one gives us the status messages of the uploading process. When we collected enough data and train the model, we also want to preprocess the data. I will talk about in a moment, but right now it's important to know that the same preprocessing pipeline that was used in model training must be employed for the inference. The usual way to guarantee that is to pickle the pipeline after training data preprocessing, make it a part of the component, and unpickle it on the inference side. Now let's talk about machine learning. The anomaly detection component contains a neural network model that allows us to calculate the anomaly score to decide whether the current behavior is normal or not. But first, let's return to data preprocessing. Our raw data is difficult to work with. We have streaming data from two accelerometers, which are differently oriented in space, and send the data with an uneven time interval, so it's not synchronized. What we would want to get is synchronized time series data, which we can work with. Moreover, we need to work with the streaming data, so we cannot batch process the dataset to allow the pipeline to work on the inference side. Also, as we work with the streaming data, we need to process it in fixed size time windows, while guaranteeing that no data separated by time fall into the same window. You can see on the screen an example of data we would like to achieve. We have created the preprocessing pipeline consisting of the following steps. Normalized axis reorients the local accelerometer's coordinate system to a global one. Normalized scales rescales the accelerometer's data so that it takes values in -1 to 1 interval. It's a standard step in the machine learning pipelines, and it stabilizes and accelerates the training process. Window transformer is the most complex step. It synchronizes the data and splits it to the fixed windows along with some additional preprocessing. And finally, drop time just drops the column with correction time. To calculate the anomaly score, we have chosen to implement a convolutional autoencoder. This is a neural network that is trained to output its training data. It, however, contains some bottleneck layers that prevent it from predicting perfectly. So it has to learn some compact data representations that allows it to do that efficiently. Of course, this representation works well only on inputs that the autoencoder saw during the training, and it works poorly on the unfamiliar data. This property makes it a good anomaly detection model. We used Keras as a training framework. After the model is trained, we need to optimize it so it can run on the gateway. During the process, the network is pruned, compressed, and possibly quantized. One possible way to do this is to use the SageMaker Neo service that can optimize network produced by different frameworks. It generates a model that can be run using the Neo ADLR runtime, which is available as a Greengrass component. Greengrass, however, doesn't restrict you in the choice of the runtime, and you can provide any that can fit on your device. So we have converted the model to TensorFlow Lite format, which is using live runtime. To calculate the anomaly score, we use a scaled mean square difference between model inputs and outputs. Now we have integrated all this in our anomaly detection component that calculates the anomaly score and put it to yet another stream. What is left is to write the anomaly score along with the data that produced it to the cloud-based time series database and visualize it. We have chosen the time stream service as it is a managed time service database that requires minimum efforts to get it run. To write to it, we used another nice feature of Greengrass, which allows us to manage a role it can assume and provide necessary permissions to the components. So we gave our Greengrass core device permissions to write to the timestream database and use the Bot3 client to write data to it. And finally, it's time to see the graphs. Grafana is a nice and now also AWS managed monitoring solution that integrates with all major databases, timestream included, and allows to visualize the data in the most appropriate and eye-candy way. And now let me show you how the solution works. I won't actually print anything, but for now I will simulate how the printer works normally. We see that our anomaly score is small. Let me now introduce an anomaly in the form of a rock G-code command that can potentially break the printer. As you can see, the anomaly score skyrocketed. This is an unfamiliar situation, after which it got back to the normal values. And here I conclude my demo. Thank you.
Thank you, Konstantin. Before wrapping up, I also want to mention that the Greengrass version 2 is open source, and you can follow and participate in the development on a GitHub. With that, thank you very much for your attention, and you can follow up if you have any question. Don't hesitate to follow up with AWS or Klika or both. We will soon publish this reference architecture with all the source code and components on both AWS and Klika sites. So again, thank you very much for your attention, and have a wonderful rest of your show.